In section 2.4, we're going to look at some relationships between parallel and perpendicular lines. So our essential understanding, what we want to get out of this section, is that you can use the relationships of two lines to a third line to decide whether the two lines are parallel or perpendicular to each other. So we're going to start out here with this first theorem, which states that if two lines are parallel to the same line, then they are parallel to each other. So for example, if I have that line A is parallel to line B, and that line B is parallel to line C, then that means that A is parallel to C. It's kind of like a transitive property for parallel lines. We've got two lines parallel to the same line, which in turn means they have to be parallel to each other. Okay. So take a look at this problem. It's a carpentry problem. Okay. Carpenter plans to install molding on the sides and the top of a doorway. He cuts the ends of the top piece and one end of each side piece at 45-degree angles as shown. Will the side pieces of molding be parallel? Okay, so the question is, will this side piece here and this side piece here be parallel to each other? Well, if we were to take these pieces here and join them, if I take a 45 and a 45, that means I would end up with a 90. So we'd have something like this, where I've got a 90 and a 90. And if I look at those two angles, they could really be thought of as same side interior angles. And if they're both 90, then that means their sum is 180. So those same side interior angles are supplementary, which tells us that the lines would be parallel. So indeed, the sides of that door frame would be parallel. Okay? So another thing to think of is that if they're both 90, that would also mean that each of the sides is perpendicular to the top of the doorway. Okay? So we know that the side is perpendicular to the top. And this kind of leads us into our next theorem. And this next theorem talks about that if we are in a plane and two lines are perpendicular to the same line, then they are parallel to each other. So I have line T here, which is perpendicular to M, and it's perpendicular to N. So since both lines are perpendicular to T, they're both perpendicular to the same line, we know that those two lines have to be parallel to each other, just like we saw in the example with the doorway. Another related theorem says that if a line is perpendicular to one of two parallel lines, then it's also perpendicular to the other. And this should be easy to see if we go back to our previous rules talking about parallel lines. If we look at our diagram here, if we know those two lines are parallel, then the angle here that's already marked at 90 degrees and this angle down here with line M, those are corresponding angles. Okay? And since the lines are parallel, we know that parallel lines tells us that the corresponding angles have to be congruent. So if we know that the first angle is 90 degrees, then we know that this second angle has to be 90 degrees as well. And if it is 90 degrees, then that in fact means that N is perpendicular to M. But rather than having to go through all of this down here using the corresponding angles theorem, this theorem allows us to take a shortcut, to know that if the two lines are parallel and the transversal is perpendicular to one of them, then it has to be perpendicular to the other. So just keep that in mind, that these theorems are really shortcuts. If I forget this theorem, I can still go back to the idea of the corresponding angles and still figure out that those angles are both going to be 90 and that I'll have a perpendicular. It's just going to take me more steps to get there. So let's look at this short proof. So in a plane, we've got line C is perpendicular to line B. We've got that line B is perpendicular to line D, and that line D is perpendicular to line A. So a lot of perpendicular stuff going on. Okay? And we want to prove that C is perpendicular to A. Well, if we look at the first two statements here, that C is perpendicular to B and B is perpendicular to D, then I have two lines that are both perpendicular to B. They're both perpendicular to the same line. And our previous theorems told us that if two lines were perpendicular to the same line, then those two lines have to be parallel. So we know that line C is parallel to line D, and our reason is that two lines perpendicular to the same line are going to be parallel. Okay? So two lines perpendicular to the same line are going to be parallel. So now, if I look, I've got D is perpendicular to A, okay? And I know that I'm trying to get C to be perpendicular to A. Well, if D is perpendicular to A and C and D are parallel, okay, then if I have a line A that's perpendicular to one of the parallels, then it has to be perpendicular to the other. So C is perpendicular to A because a line perpendicular to one of two parallel lines is perpendicular to the other. That was another one of those theorems. Okay? So again, I could figure all of this stuff out using the theorems about parallel lines and the special angles. These theorems that we're doing with the parallels and the perpendiculars are merely shortcuts. If I were to use the corresponding angles and all that, this proof becomes twice as long, 6, 7, maybe 8 steps. But using these theorems, I'm able to take these shortcuts. Okay. So, in the last problem, we showed that C was perpendicular to A. Okay, so that if line C were to extend across here, we know it would be a perpendicular. Could we also conclude that A is parallel to B? Okay, and if so, how would we explain that? Okay. Well, if we look here, we see that A is perpendicular to D, and we've got that B is perpendicular to D. Okay, so if I have two lines perpendicular to the same line, one of our theorems said that that must be parallel. So the answer here is yes. And our reason is if two lines are perpendicular to the same line, then the two lines are parallel. Okay? And again, I could get there through, angles being 90 degrees and their corresponding angles, and now they're congruent, so the lines are parallel. Takes me 3 or 4 steps, or I use this theorem for my shortcut, and it's one step and done. Okay? So it's an important concept to learn these theorems. These theorems provide us with our shortcuts when we're trying to prove things or trying to make connections. Okay? So we'll go through, we'll answer any questions you have over these in class tomorrow, maybe look at another example, and then we'll work on some problems in class. We'll see you then.